Okay, so here's a problem that we're going to work out. Calculate the pH of a 0.20 molar acetic acid solution. Alright, so pH problem. Now, acetic acid, so if we want to know the pH, that's basically the concentration of the hydrogen ions in the solution. Alright, so basically this acetic acid's in the solution, it's going to deprotonate and release these hydrogen ions, and that's what's going to make the pH. And we know that it's going to be a weak acid, meaning that it's a reversible reaction, donating the proton and taking it back. We know that it's a weak acid because it has a Ka. So the first thing that we need to do for this is we need to write out the equation or the chemical reaction that's happening. So acetic acid, CH3COH plus some water, because we're throwing it in the water. It's reversible. I have that hydronium ion when it takes up the proton, and then what's left over is that. Alright, all of that looks good. We have the acetic acid and the water. Then this hydrogen is donated to the water, making the hydronium ion, and then we're left with this. Now hydrogen has a positive charge, so this becomes positive, and this is left with a negative charge. The overall charge here is 0, and the overall charge here is still 0. So it looks good to me. Now, this reversible reaction is going to be going back and forth until it reaches an equilibrium. That is when it's going to stop, and that's when we'll have a constant concentration of this hydronium ion, which, don't forget, this hydronium ion is equivalent to H+. Alright, so I might be using them interchangeably. So, like I was saying, the reaction will be going back and forth until it reaches equilibrium, and then when it's steady, that hydrogen concentration, that is what will determine the pH. So, when you say equilibrium, then we know that we're going to be using that equilibrium constant, which for this one will be H+, conjugate base. Remember, equilibrium constant is the products over the reactants, or concentrations of the products over the reactants of just aqueous solutions and gaseous. Alright, and as you can see, I didn't use the hydronium ion, I used the H+, but you can interchange them, or change them out. So, and when we do this, the equilibrium constant is the same thing as Ka, and that was given, Ka. If it's not given, you should probably look it up. Now, alright, so let's see. We know once we add this acetic acid, it's going to be going back and forth. We start off with a, actually I need to rewrite this equation. I shouldn't have wrote that there. Alright, there we go. Redrew it. So, like I was saying, we're going to add some acetic acid. We add some of this. In fact, we're adding 0.2 molar of this. And now not that whole thing is going to stay 0.20, because it's going to donate some hydrogen. Some of it's going to become the conjugate base. So we need to figure out how much of this it's going to lose. And when we're doing a problem like this, we do this method called the ice chart or ice table, something like that. And basically, what we have to do is we have to find the initial, the change, and then the equilibrium. Alright, I know that's ugly, but we all know what it means. Alright, so the initial concentration of all of these, the change, and the equilibrium. Alright, so let's start off with initial. So the initial concentration of acetic acid was given in the problem. I won't scroll up, I'll just tell you. 0.20. Okay? Now the initial concentration of the water is a lot. We don't need to do that because it's not in the equilibrium constant equation. The initial concentration of the hydronium ion is 0, because we're talking, when we say initially, we mean like right when we add the acetic acid. Nothing's happened yet. Hasn't dissociated at all. So 0, and if it hasn't dissociated, This is also 0. Alright, now the change. So that means how much is the acetic acid going to lose or gain to reach equilibrium. The change, I don't know what the change is. So what we're going to do is we're just going to put minus x. And the reason why I put x is because we know once we add that acetic acid into the solution, a certain amount of it is going to dissociate and change into the conjugate base over here. So that means we're going to lose a certain amount of this concentration. It could be 0.1, 0.2, point whatever, have no idea. We're just going to put x. Now for the water, that doesn't matter either. And then for the hydronium ion, don't know that either. But what we do know is that however amount the acetic acid is going to lose, the hydronium ion will gain. If we're saying minus x is how much the acetic acid is going to lose, then we know that hydronium ion is plus x. Yeah, that's pretty cool, right? And then the same thing for the acetic acid, because they're both coming from the same thing. Alright, so now equilibrium is basically going to be 0.2, what we started off with, minus x. And then the hydronium ion is going to be, when you do the equilibrium, you're basically just adding the first two rows. So the next two are just going to be x and x. Alright, so we're almost there. Basically what we just figured out is at equilibrium, the concentration of the acetic acid is 0.2 minus x. And at equilibrium, the concentration of the hydronium ion is x. And the concentration of the acetic acid, or conjugate base, is x. Okay, so we haven't figured out too much yet. But when we go to the equilibrium constant, Ka equals the concentration of the H plus, or the hydrogen ion, at equilibrium, which we know that is x. Okay, so I'm just going to replace that. X. Okay, and the concentration of the conjugate base at equilibrium, which we have something for that too, it's x. So I'm going to put that there too, x times x. And then divided by the concentration of acetic acid at equilibrium. That's the point of the equilibrium constant, at equilibrium, which is 0.2 minus x. So I'm going to replace that there. 0.2 minus x. Alright, so we're all smart here. I'm going to change x times x to x squared divided by 0.2. Oh man, I messed up. There we go, 0.2 minus x. Okay, so the next thing, let me, before I say anything else, let me just write it a little more prettier right here. So the equation we have now is Ka equals x squared divided by 0.2 minus x. Okay, looking good so far. Man, we've done a lot of work. I'm already forgetting like what we were doing in the first place. Calculate the pH. Oh yeah, pH. So the way we were looking for the pH is by finding the concentration of the hydrogen ion. So the concentration of the hydrogen ion is the same thing as the hydronium ion, which is what we have in the equation right here is x. So basically, if we figure x out, we can figure out the pH. Okay, so now that we're back on track. Alright, so Ka equals x squared divided by 0.2 minus x. Now remember, we're looking for x. And luckily, they gave us Ka in the beginning, you remember? So that means that 1.85 times 10 to the negative fifth, that's Ka, which they gave us, equals x squared divided by 0.2 minus x. Alright, looking good. All we have to do is solve for x. It's not even a chemistry problem anymore, it's just algebra. And you know what? There's this assumption that you can make when you're doing a problem like this, is that this x right here, you can actually just erase it. And I'm going to explain. So basically, remember this x, where this came from? 0.2 minus x? That came from this right here, 0.2 minus x. And that minus x is how much, it's the concentration that the acetic acid loses once we throw it into the solution. So basically what happens is that the amount it loses is really, 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 really small. So let's pretend it's like 0.000001. So 0.2 minus 0.000001 is about 0.2. So you can basically change this up to, put it right here, 1.85 times 10 to the negative fifth equals x squared divided by 0.02. So we just got rid of the x. And that makes the problem a lot easier. Now there are some cases where you can't get rid of this x, and that's when you have to use the quadratic equation, which I'll probably do in another video. I'm running out of time here, but in this case we get to do it the easy way, which is how you do it most of the time, so it's okay. Alright, so we just got to rearrange this to solve for x. So basically, I mean, I don't know if you want an algebra lesson, but 0.085 times 10 to the negative fifth times 0.2 equals x squared. So that means 1.85 times 10 to the negative fifth times 0.2, or the square root of all of it, equals x. Okay, we throw that in your calculator. I can't do that in my head right now. You know, let me get a calculator. Alright, I got it. Let me do this. Okay, so x equals 1.9 times 10 to the negative third. Alright, so we found x. And you're thinking like, Josh, why were we looking for x again? Well, I'll tell you real quick because I got time. Remember, x equals a lot of things, actually. Where's my pointer? Here we go. X equals the concentration of the hydronium ion at equilibrium, and the concentration of the conjugate base at equilibrium, and it also equals the amount that the acetic acid loses to reach equilibrium. And I said a lot there, but all that's important is that X equals the concentration of the hydronium ion, in which in the beginning, if you remember, I told you the hydronium ion is equal to the hydrogen ion, and if you know your chemistry, you should know that when you take the negative log of H plus, or the hydrogen ion, concentration of the hydrogen ion, that equals pH. pH, and if you remember, pH is what we're looking for. So we have the concentration of the hydrogen ion, and we have this equation that I wrote for you, so all we got to do is throw it in there. Alright, here we go. Negative log of the hydrogen concentration, which is 1.9 times 10 to the negative third. That equals pH, and it turns out to be 2.72. Alright, I think we did it. There's your answer. So let's go back to what was the question? Calculate the pH of a 0.20 molar acetic acid solution. We just found the pH, which is 2.72. And I have one more minute, so I'll try and do a quick recap. So basically, we throw 0.02 molar into the solution, it dissociates, and it loses a certain amount, which becomes a hydrogen ion, and we have to find that concentration at equilibrium, so we use the equilibrium constant, and then to find the amount that it actually does use, we use this thing called the ice chart, which I have right here, the initial, the change, and the equilibrium. So the initial is what we start off with, which is 0.2, and 0 for these, because initially we don't have those yet. But then a change happens, we lose X amount and gain X amount for each one, and then those put together equal those at equilibrium. We throw it into the equilibrium constant equation, and we get this thing going on here, and then the minus X is negligible, so we can get rid of that, and we're left with where are we at? So if we get rid of the X, we're left with this right here, and the Ka, which is the acid, the equilibrium constant for the acid, was given. So then we have this equation, we just solve for X, which equals the hydrogen ion concentration, and once we get that, we take the negative log of the hydrogen ion concentration, gives us pH, and so 2.72. There we go. See you next time.